Hi everyone. In this video, I'm going to discuss about our next module in the CCNA course, which is module 12, and we are going to deal with IPv6 addressing and also subnetting issues. In the last video, we covered about IPv4 addresses, types of addresses, and subnetting, how to do it in IPv4, and we also did some packet tracer activities to get used with it. So let's start this module. This module is pretty important because IPv6 is the future and we need to be future ready. Working with IPv4, subnetting IPv4 is okay, but moving towards into the future where big data and IoT are different, numerous number of devices are being connected to the internet, we require a lot of address space and IPv4 is not going to fulfill the requirement. That is the reason we have to go to a new particular version of IP which solves the primary problem of IPv4, which is the lack of addressing space. So that is the reason we come up with IPv6. In this module, we are going to cover the different topics which include what are the issues with IPv4, the how do you actually represent an IPv6 address, what are the different types of IPv6 addresses, what do you mean by a global unicast address, link local address, how do you do the dynamic addressing for GUS and LLAs, what are the different IPv6 multicast addresses, and how do you subnet an IPv6 network. And let's go into this. First, let us talk about why we should go for IPv6. What is the reason? Now, I usually feel that if something works well, people generally don't tend to go for something else. But unless until there is an issue with the current technology that we are using, we tend to go for a new one. Similarly, the main problem with IPv4 is there is not enough space left in IPv4. It is actually by the, if you can see on the slide over there, the dates given for exhaustion of IPv4 address space are long gone. And now IPv6 being a successor to IPv4 has got a much larger 128-bit address space. There is the while designing IPv6, numerous things have come into play which actually try to solve the different issues that are there with IPv4. Now if you see here, the internet keeps on evolving and the type different and the number of devices that are actually getting connected to the internet keeps on increasing. There is no way that we are going to limit the number of devices. And also with IPv4 there are issues regarding to the usage of network address translation and the port address translation techniques, the end-to-end connectivity being not maintained. All those issues are actually solved by IPv6. And there is, because it is going to take some time for us to go completely from the transition to happen from IPv4 to IPv6 completely. In the meantime, IETF has created various protocols and tools to help the network administrators to migrate their networks to IPv6. These migration techniques are actually divided into three categories. The first category is having a dual stack where the devices run both IPv4 and IPv6 simultaneously. The second one is tunneling, which is nothing but transporting an IPv6 packet over an IPv4 network. Here, this IPv6 packet is encapsulated inside an IPv4 packet. The third one is translation, where a type of translation protocol, something called as Network Address Translation 64, NAT64, which allows an IPv6 enabled device to communicate with IPv4 enabled device using this translation technique. It is much similar to the how we do the network address translation in IPv4 addressing. So let us see how an IPv6 address is actually represented. All of you are aware that in IPv4, we have 32 bits and they are represented in decimal notation where these 32 bits are written in 4 octets. Here, as IPv6 addresses are 128 bits in length, and hence we chosen the hexadecimal format, which is pretty similar of writing decimal to binary. And hexadecimal is easier for human beings to write down. And IPv6 addresses are not case sensitive, and they can be either written in lowercase or uppercase. Generally, the preferred format of writing IPv6 address is this, where these we actually say divide each part into columns, and this X is nothing but 4 hexadecimal values, and also we call them as hextets. So we call in IPv4 we used to call them as octet, and here we call them as hextet. So 1, 2, 3, 4, 5, 6, 7, 8. 8 hextets, 8 16s, and we get the 128 bits. So this is an unofficial term used to refer to a segment of 16 bits or 4 hexadecimal values. And in order to give you a glimpse of how IPv6 works or how IPv6 address looks like, there are two examples that I have written down here. You see 2001 colon 0 db8 colon 000 colon 41s colon 000 colon 000 colon 000 colon 0200. Similarly, now even for human beings, even if you write in hexadecimal format, this is quite a lengthy representation of IPv6, and it is not going to be easy to remember these addresses. Hence, we have two techniques in order to make it easy for representing these long addresses. So let me show you how it is done. The first rule or the first technique that we use in order to reduce these the length of the IPv6 address and to represent it in a much more easier manner is to omit any leading zeros. If you take these examples, if you see here 01AB can be represented as 1AB. This 0 towards your left hand side can be omitted. So 09F0 can be represented as 9F0. Please do not misunderstand that these zeros which are on your right hand side can be omitted. You cannot omit them. Only on the front part or towards your left hand side are the first zeros which come towards the first can be omitted. And 0A00 can be represented as A00. And 00AB can be represented as AB. As I said, this rule only applies to leading zeros, but not to the trailing zeros. If you remove the trailing zeros, your address won't be the same. You are actually changing the address. Now, if you see here, I have given a small example for us to understand. So 2001, 0db8, colon 000, colon 1111, colon 4 zeros, colon 4 zeros, colon 4 zeros, colon 0200. If this address, now once you apply this rule, and if you write it down, if you check it out here, 2001 is the same. I have a leading zero here, which I can omit, db8, colon. Here there are three leading zeros which I can omit. So 0, 4 ones, colon. Once again, I can omit these three zeros, which I can get 0 here. So once again, 0, I can omit these three zeros. These three leading zeros are gone. And then this one leading zero is gone. So colon 200. This is the first rule. Now, in order to even efficiently represent it more in a better manner, we have the second rule where we can actually use a double colon. But please remember, in any IPv6 address, only once a double colon should be used. Under no circumstances, you should be seeing two double colons in an IPv6 address, which leads to an error. So a double colon is nothing but where you can actually place it once in an IPv6 address, and it can replace any single or contiguous string of one or more 16 hex states consisting of all zeros. Now, if you have a long string of these zeros, I can actually replace them and simply place a double colon there. That's all. As simple as that. If you check out this example, now in the earlier one, which you got 2001 colon db8 colon cafe colon 1 colon 0 colon 0 colon 0 colon 1. Now, if you see here, there is a string of three zeros here, right? That means this is a 404040, right? 12 zeros. Now I can remove all these and I can simply represent them as a double colon here. Hope you understand. So this double colon can be used only once within an address, and it can actually replace if it is a single or a contiguous string of one or more 16-bit hex states of all zeros. Okay. Now the double colon, as I said, can be used only once within an address. Otherwise, there will be more than one possible resulting addresses. As I said, it leads to an error. Now let me take the same example that we did for rule 1, and now let me show you how this IPv6 address can be now represented or can be represented in an easier manner. So 2001 colon. So here is a 0 there, db8 colon. There is a 4 zeros here, 0 colon 1111, and there is a string of zeros here, right? So what did I do? I simply removed all these zeros and I simply placed a double colon here. 200. You could ask me, sir, why can I do this for this also? Yes, you can, but if you remove, if you place this double colon here, you are actually omitting more number of zeros here. So the ideal place of placing this double colon is here. You can actually also write them as if 0 db8 double colon 111, and then you have to write all these zeros again, because you cannot use a double colon again. A double colon can be used only once. So use it wisely, so that you can compress an IPv6 address to its smallest possible way of representation. Now, these are other examples that I got here for you. And if you can see, so this is all four zeros, four zeros, four zeros, and if I omit all the leading zeros, this is how once I apply rule 1, this is the output that I get. And here it is the last one, the last column is 0 0 0 1, and if I remove the first three leading zeros, I get a 1 here. So ultimately this IPv6 address can be easily represented as double colon 1. Yes, it is double colon 1. That's it for this address. And if I move on to the second example, here we have the system, we have the address as 20010 db8 2213. All these things are written. Now if I put the rule 1 2001, this 0 can be omitted. Fine. This is the same, this is same, this is same, and these four zeros, the first three zeros can be omitted. So I can write only a 0. And in this, the first three zeros can be omitted, then I write a 0. And here the first 0 can be omitted, 101. And then onwards, the string of zeros are only here. So what do I do? After this particular 6677, I can simply place a double colon and then 101. Similarly, if you take this example, 1031, 1976, these three zeros omitted, 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 I have to place a 0 here, and this 0 omitted. Fine. I can only have a single string of four zeros here. So what do I do? After 4, I put a double colon and 101. Similarly, we have lots of examples in order to fill this up, but I suggest you try one for yourself in your NetAcad account. There are many CYU quizzes which will help you to understand and apply these two rules better to write or to represent the IPv6 addresses in a much compressed format. Okay, now let's move on to the different address types of IPv6. What are the different address types that are there in this IPv6? Now, broadly categorizing the addresses, we have three types. One of it is called as unicast, the second is multicast, and the third one is anycast. You know, unicast, it means simply one-to-one communication. These unicast addresses uniquely identify an interface on an IPv6 enabled device. Multicast is used to send a single IPv6 packet to multiple destinations. These both are same, much more very similar to what you do in IPv4. Whereas in Anycast, this is an address that can be assigned to multiple devices. What usually happens here is, if you send a packet to an Anycast address, this is actually routed to the nearest device having that address. So whichever device is having this Anycast address, the packet is first delivered to that, which is closest or which is nearest to it. And from that point onwards, it will be delivered to the others. Here, one thing you have to observe is IPv6, there is no broadcast, but there is something called as an IPv6 all nodes multicast address, which actually gives you the same set of result. So to get a overall idea, if you see here in IPv6 address, as I told you, the three broad categories that we have are unicast, multicast, and anycast. In unicast, once again, you have different categories. So global unicast, GUA, LLA, loopback address, unspecified. This is not used anywhere. And you have unique local, you have embedded IPv4 addresses. And in multicast, once again, we have the well-known transient solicited node and anycast addresses. Okay. So let me just go through each one of them in detail. In an IPv6, once again, we have the network portion and the host portion. So the prefix length is actually represented in the slash notation that we used to do in the prefix notation of IPv4. Here it is also used to indicate the network portion. It's quite similar to what we do in IPv4. The IPv6 prefix length can range from 0 to 128, but usually the preferred or the recommended prefix length for most of the LANs using IPv6 is /64. That means these first 64 bits of the 128 represent the network portion, whereas the next 64 bits represent the host portion. Usually, we don't say network and host here. The first 64 bits, we call them as the prefix, and the next 64 bits, we call them as the interface ID. And the reason behind using of 64 bits as your prefix is because SLAAC, we'll discuss it later on, stateless address auto configuration protocol, it uses the 64 bits for interface ID, which makes it provides the dynamic addressing of the GUA. We'll discuss it. So these are the different types of IPv6 unicast addresses. So if you see here, I have given you a small graphic where in these IPv6 unicast addresses, the different types are present over there. The first one being the global unicast one. The second one is the link local. So of these two, you have to very much understand that This global unicast address, it is very much similar, or it does the same job as the public address in your IPv4. This is the one which is globally routable, or where you connect to the internet, and it is also globally unique. Whereas the second one, something called as a link local address, LLA, what we do is, this is actually mandate. It is required for each and every IPv6 enabled device, and this is specifically used to communicate with other devices on the same link. So these LLAs are not routable, and but are only confined to that particular link only. So unlike IPv4, IP for that usually a device of IPv4 will have only single address. IPv6 addresses are actually having two unicast addresses. So one is UA, the other one is link local. A single interface can have both. Okay, a single interface will have both. So one of them is UA and the other one is LLA. UA is similar to your public IPv4 address, which is globally unique and internet routable. That means you can actually route them over the networks. Whereas LLA, this is required for each and every IPv6 enabled device, and it is used to communicate with other devices on the same local link. These are not routable, and they are only confined to that particular link only. You know what loopback address is? So this loopback address is actually used to check whether the TCP IP protocol suite has been installed on your system properly or not, whether it is working or not. So :1/128. And this is the unspecified address. Actually, this is a small typo mistake here. I think it's 0. Okay, that's :, which we don't use it for anywhere. It is called as an unspecified address. And about this unique local address, if you see here, these unique local addresses are having similarities to the private addresses of IPv4 at the same time, but are different. As I said, they have similarity to the RFC 1918 private addresses for IPv4, but there are significant differences also. They are used for local addressing within a site or between a limited number of sites. These unique local addresses, which are actually in the ranges of FC00:7. Once again, the /7 is your prefix length. FDFF:/7. This is the range of your unique local addresses. They are actually used for devices which they never need to access the another network. They can only within the same network only. These unique local addresses, they are not globally routed, but also they are not translated to a global or GUA or the global IPv6 address. In our IPv4, when we assign a private address, usually when the router does the NAT translation, the private addresses are then mapped to a public IPv4 address. But for unique local addresses, it does not happen. The unique local addresses are never translated into a global IPv6 address, and also they will not be globally routed. They are only used for local addressing within a site or between a number of sites, and they are generally given for devices which never need to access another or a different network. This is regarding your unique local addresses. And if once again, this is the structure of a GUA. IPv6 global unicast addresses are globally unique and are routable on the internet. So currently, as of now, the GUAs, the first 3 bits of all the GUAs that are available now are 001 or 2:0:0:3. They are all the ones which are assigned. So if you see here, these are the first 3 bits: 001 or 2:0:0:3. And currently available GUAs begin with a decimal, 2 or a 3. So this is one. This is actually we are currently using only the 1/8 of the total available IPv6 address space. If you see here, there are 3 parts in a GUA. The first part is your global routing prefix. The second part is your subnet ID, and the third part is your interface ID. In this global routing prefix, right now we are actually using these from here 001 to 0011, and this is the range of addresses that we are currently using nowadays. And the subnet ID will actually tell you what subnet it is. And whereas the interface ID is pretty much similar to your host address. Now, you see here, the first one is your global routing prefix, is the prefix of the network portion of the address that is assigned by your ISP to a customer or to a site. The global routing prefix will vary depend on the ISP policies. So according to your internet service provider, you get the global routing prefix. Whereas the subnet ID is used by an organization to identify subnets within its sites. Now, if you have an GUI and if you want to do the subnetting according to your requirements, this subnet ID will come to your aid. Whereas the last portion in your GUI, which is your interface ID, it is equivalent to the host portion of an IPv4 address. It is strongly recommended that in most cases, /64 subnets should be used, which creates a 64-bit interface ID. We will discuss that. I'll show you how subnetting is also done. So now let's move on. That is regarding your GUIs, that is your global unicast addresses. Now let's move on to our LLAs, which are link local addresses. As I told you, each and every IPv6 enabled interface must have an LLA attached to it. So these LLAs enable a device to communicate with other IPv6 enabled devices on the same link and only on that particular subnet or that particular link. If you are having a packet with the source or destination addresses as LLA, they will not be routed. They cannot be routed. And as I said, each and every IPv6 enabled network interface must have an LLA. If LLA is not configured manually on interface, the device will automatically create one. I'll show you how it is actually going to get dynamic assignment of LLA. And all the IPv6 LLAs are in the FE80:/10 range. The /10 indicates that the first 10 bits are these, which are written down here. The first hex state has a range of this FE80 to this, and the last range is FEBF. So from FE80 to FEBF, this is the range of all the IPv6 LLAs. Okay. Now let me show you. First, let us talk about static or manual configuration of your GUI and LLA, and then we will go for the how the device can get dynamic allocation. So let me start with your static allocation. Once again, we have very much very close similarities to how you assign an IPv4 address to a router interface. Here, instead of once you type in the interface command, and rather than simply typing in IP address, here what we do is we type in IPv6 address. Here we type in IPv6 address, that's all. And then no shutdown. And earlier in IPv4 address, we used to type in the subnet mask, but rather than the subnet mask, what we do is we type in the entire IPv6 address here and then followed by the prefix. Then automatically this address will be assigned. This is the simplest way of assigning an GUI to an interface. See, for this particular router, you have 3 interfaces, and for each interface G0/0/0, I assigned this address. For this G0/0/0/1, and this network ACAD:2/1, this is the interface. This is the IPv6 address that I gave. And for this interface S0/1/0, this is your third network, and I gave the address to this. It's pretty similar to what we do in IPv4 addressing. The only difference being you have to type in IPv6 address and you don't type in the subnet mask. You simply write directly the prefix length. So if you go for a host, it is very easy. Once again, just like in IPv4, you have the specific boxes for that. You simply copy paste the IPv6 address, then you give in the subnet prefix length. Earlier, we used to type in the subnet mask for IPv4, but here we need not do that, because we have the same, we have the idea of going directly writing down the subnet prefix length, and then you give the default gateway. That's all. It's very much similar. And if you use the DHCP version 6 or SLAAC, this LLA of the router will be automatically specified. I'll show you how it is being done. And if you see, the GUI or LLA of the router interface can be used as a default gateway. In IPv4, we used to give the first address, or the address, the first host address that we can use to the default gateway interface. But here what we do is we either actually give the GUI or the LLA of your IPv6 router. Okay, I'll show you, don't worry. This is the static configuration of a link local unicast address. Once again, the most and the best thing for you to do here is you type in the interface, whatever interface you want to assign the address for, and then you type in the IPv6 address. You enter the link local address, then followed by the link local thing. If you don't write link local here, it will not be assigned to this interface, and you have to mention link local here. So IPv6 address, your IPv6 address, and then the link local, and then perform the exit. So for these 3 interfaces, I did assign the I did the static configuration of a link local unicast address by specifying this link local towards the end. So if all these are within the range we just discussed. All these are within the range that we just discussed. This is the manual configuration of your link local address for an IPv6 interface. Just go to the interface command, then do the IPv6. I will be posting the videos for your packet tracer activities for this module also. So just keep an eye out. I will show you how to do this. We have different, I think 3 different packet tracer activities where you can work with the assignments of GUA, LLA, static and dynamic assignments. We'll work with that. So let me move on. Now, the static configuration is pretty easy. Just you type in the command and then it will be done. So what about the dynamic addressing? How it is being done? So if you remember the ICMP protocol that we discussed in module 9, I think. Yes, we discussed ARP and ICMP in module 9. Internet Control Message Protocol version 6, we have 2 different types of messages. One of it is called as a router solicitation message. The other one is called as a router advertisement message. So let me call it RS and RA. So RS messages are actually sent by a host device to discover where the IPv6 routers are. So it's literally asking, who is the IPv6 router here? Who is going to help me? That is called as an router solicitation or an RS message. The other message, we call it as a router advertisement message. These messages are actually sent periodically by the IPv6 enabled routers to inform the host on how to obtain an IPv6 GUA and other network information. So a router solicitation message is actually sent by a host requesting the presence or the information about any IPv6 routers, whereas router advertisements or RA messages are actually sent by the routers to inform hosts about the information on getting the GUAs and other network information. So you might ask me, sir, what type of information are they looking for, sir? The most important information is what is the length of the network prefix, and what is the prefix length, what is the default gateway address, and also the other information including the DNS addresses and the domain names. The RA message does provide 3 methods for configuring an IPv6 GUA. So for dynamic configuration of the IPv6 global unicast address, we have 3 methods specified, which these 3 methods are actually given by your router advertisement message. I'll show you what these things are. Now, before we go there, first you have to remember that these RA messages are actually being delivered on your IPv6 router Ethernet interfaces. By default, an IPv6 interface is not enabled. So to enable a router as an IPv6 router, you have to type in the command IPv6 unicast routing. Unless until you enter this command, your router might not be able to receive and understand these RA messages. So before we start working with IPv6 on your router, we have to enter this IPv6 unicast routing command. If you don't enter this, your IPv6 routing might not work. So please do keep in mind. Usually when we do the packet tracer activities or even in your exams, it is a common practice to forget about this because we are very much might be totally involved with subnetting and other things. But please remember, first start your work on IPv6 by entering this command. And as I said, the RA message contains a lot of information about network, and this information is going to contain about what is the network prefix, what is the actual network prefix, and what is the prefix length, what is your default gateway address, which might be the LLA or GUA of your router's interface, and also what is the DNS addresses and what is the domain name. And as I said, there are 3 actual methods through which you can do the dynamic configuration. The first method is called as SLAAC, SLAAC, stateless address auto configuration protocol. And here we will discuss each one in detail. The second one is SLAAC with a stateless DHCP version 6 server. The third one being, it is called as a stateful DHCP server. There is no SLAAC here. Okay. Now, if you want to have a vague idea of what are these 3 methods and how these 3 methods work, the first method is something called as SLAAC is saying that the router literally saying, I have everything that you need, all that information that I just told you, including the prefix length, and the default gateway address. The router advertised message itself provides it to the host. Whereas the second method, SLAAC, which the stateless DHCP say version 6 server, what the router advertisement message says is, it provides you information about the particular router, but it says that you have to go to a DNS server and you have to go to a DHCP server to get the other information like your DNS address and a domain name. Whereas the third one, which is called as a stateful DHCP version 6 server, it says that, okay, I'm only going to give you the default gateway address, but for all the other information, including the network prefix, prefix length, and all the other information, go and get it from a DHCP stateful server. So let us see those things in detail. Now, this is the first method called as SLAC, stateless address auto configuration protocol. And if you see, this is a method that allows a device to create its own global unicast address without the services of a DHCP v6. If there is no DHCP server present in this network, still a host can configure its own GUA address. This is through SLAC, which this SLAC information or the information for generation of this particular GUA address is given by your RA message or the router advertisement message. So by default, the RA message suggests that the receiving device use the information in the RA message to create its own IPv6 GUA and other necessary information. So what does it provide, sir? So when you go for this method one, that is your SLAC method, what happens here is the client device uses the information in the RA message to create its own GUA. So what information is present? The first thing is it gives you the prefix, which is used here. So this is one. The prefix is used and it says that you generate your own interface ID. You generate your own interface ID, which is 64 bits in length. But there are two methods for generating this interface ID. The first method is called as EUI64. EUI64. The other method is a just random generation of a number. So if you are using the SLAC method, what is happening here is the router advertisement message provides you the first prefix of 64 bits. And for the next 64 bits, it is saying that you generate it by yourself. It doesn't matter if you are using an UI64 or a 64-bit random number, but you have to generate it on your own. Okay. So let's go to the second method. I'll explain what EUI is. Give me a couple of minutes. So the second method is something called as SLAC and stateless DHCP. Here what it says is the RA message suggests the devices use the following. SLAC to create its own IPv6 GUA, and it does provide the router's LLA, which is the link local address, which can be used as a default gateway address for this particular host. And then this host is to consult the stateless DHCP version 6 server to obtain the information such as the DNS server and the domain names. So this RA message does provide some information, but to get complete information, this host has to also consult the stateless DHCP server and then get the information. I just wrote these things down. You can just have a read for yourself. So the RA message does provide the prefix, prefix length, default gateway, whereas the DNS information will be taken from the DHCP server. Whereas the third method, which is the stateful DHCP message, where it says that the router provides only the default gateway information, and for all the other information such as your prefix length, your network prefix, and DNS names, all these things, it has to be taken from the DHCP6 server only. The router and the advertisement message only provides the default gateway address, but it says that go get the other information from a stateless DHCP server, which is provided in the network. So this is your third method, which is called as you are going to create your own GUA from a stateful DHCP version 6 server. Now, what is this UI64 process, and how do you randomly generate it? It is also pretty much simple, to be frank. Now, when the RA message is either SLAC or SLAC with stateless DHCP version 6, the client has to generate its own interface ID. This interface ID is actually 64 bits in length. The client knows the first portion for the 64 bits from the RA message. Then how do you? These 64 bits are created in two ways. There are two ways where you can actually use to create this 64 bits. The first way is something called as UI64. This is a straightforward one. UI actually stands for Extended Unique Identifier Process or modified UI64 process. Here what you do is you have your 48-bit MAC address, right? You have the 48-bit MAC address, And if you remember properly, the 48-bit MAC address does have the 24-bit OUI and then the 24-bit host part. This is what the device identifier part. Now you separate these two parts. You separate these 24 bits and in between insert something of a 16-bit value which is called as FFFE. And also you invert the 7th bit, whatever it is. If it is a 0, do it as a 1. If it is a 1, do it as a 0. So let me show you this process. It is much more easier if you see the diagram over here. It's much more easier. Now this is your 64-bit. This is your 48-bit MAC address of the device. This is the MAC address of, this is a 48-bit MAC address of your device. Okay. Now what I said, divide them into two parts. Simply write these 24 bits. This is your OUI. Okay, which actually identifies the device manufacturer, and this is the device identifier. Once again, you have both the 24 bits. Okay, now insert 16 bits which are FFFE. This is F is nothing but all ones, 4 ones, 15 F, insert them, and in the next step simply revert or flip this particular 7th bit, whatever it is. If it is 0, flip it to a 1. If it is a 1 here, flip it to a 0. Then write it down. This is your 64 bits address. That's all. It's straightforward. This is the 64-bit. This is the 64-bit interface ID portion that is added now. That's all. This is your EUI64 process. You take your MAC address, cut it into half, put it into two halves, insert FFFE in between, and then flip the 7th bit in your first in the 7th bit, and then whatever you get, simply write it down there. That's all. As simple as that. And what about the random generated, sir? And from Windows Vista, all the operating systems started using the randomly generated interface IDs. So you create a random interface. You might get a doubt, sir. What happens if two devices create the same random number? That is the reason we have something called as DAD, duplicate address detection scheme, which is very much like as an ARP broadcast, ARP request reply service. If I create a number, or if I create my like this, if in this particular example, it is shown in the yellow color. So this is your prefix portion or the network portion, which is obtained from your router advertisement message. And these 64 bits, I created it from a random number. But to just ensure, or to just be on the safe side, that okay, fine, I don't expect others to create the same random number. I will simply address this, or I will send this particular address as a broadcast, so that if any particular station also does have the same address, it will simply say, please wait, I do have the same address. That process is called as DAD, duplicate address detection. So it actually ensures that the address that you created is unique. That's all. Nowadays, even the Windows 10 does not use UI64 anymore. It actually uses the randomly generated interface ID with your network ID, which you receive from your router advertisement message. Okay. So now let's see, that is regarding your dynamic assignment of the GUIs. Now let's talk about how do you get the dynamic addressing for the LLAs. So you know that how the LLAs are done here. If you see, we discussed this. All IPv6 interfaces must have an IPv6 LLA. LLAs also can be configured dynamically. Once again, here you come across the UI64 process or a random generation of the 64-bit number. If you remember, all LLAs actually start using this prefix FE80:10. Write down FE80:10 and then generate the 64 bits of your interface ID. Attach it to here. That's it. Your LLA is done. I'll show you an example. Now, if you see, this is the UI generated interface ID. This is your network prefix. This is the 64-bit ID that is created using UI64. This is the FE80 part from link local addressing, and whatever is here, you copy it here. That is your link local address. That's all. It's straightforward. Similarly, if you use a random number, the same thing. Whatever random number that you have generated to get your 64 bits interface ID, you simply copy paste here. You get your LLA address. It's pretty simple. This is called the dynamical assignment of LLA. Okay. Now, usually in Cisco routers, what it does is by default, the Cisco routers use the UI64 to generate the interface ID. And this just as I shown you, by default, they actually do it and assign it as the LLA address. If you see, if you use the show commands to get the IPv6 interface brief, if you see, this is the address that has been generated using UI and it is actually kept here. If you see 7279, sir, there is a different number, there is a different number. Please remember that we invert the 7th bit here. So once we invert the 7th bit here, you get 7279 colon B3 because I have to divide it here. And then you have to add FF, FE and then put the remaining parts. That's it, done. This is how a Cisco router creates its dynamic LLA. To verify the IPv6 address configuration, you use the same show commands that we used in IPv4. You should get used with the show commands by now. Just type in show interface. If whatever interface you want to verify, just type in show interface gigabit ethernet or G0 by 0, whatever interface you want to type in. And the best thing for me is show IPv6 interface brief, which gives you the details about the addresses that are assigned on these interfaces. So now it's time where we need to talk about the different multicast addresses of IPv6. So as we were discussing, the IPv6 multicast addresses do have the prefix of FF0:8. Basically, there are two types of IPv6 multicast addresses. The first one we call them as the well-known multicast address, and the second one, the second category is the solicited node multicast addresses. Now, with the well-known IPv6 multicast address, once again we have two common IPv6 assigned multicast groups. These addresses are actually assigned and are reserved for predefined groups of devices. If you understand, there is the first group which is FF02:1, which is an all nodes multicast group. This group is which is actually default by default all the IPv6 enabled devices do join here. So a packet sent to this particular group is received and processed by all the IPv6 interfaces on the link or network. This is the one, FF02:1. This we call it as an all nodes multicast group. Whereas the second one, we call it as FF02:2, which is actually joined by all the IPv6 enabled routers. That's why we call it as an all routers multicast group. This is a multicast group that all the IPv6 routers join. So a router becomes a member of this group when it is enabled as an IPv6 router. I told you about the command that we need to enter in the very first, when we start working with IPv6, something called as an IPv6 unicast routing in the global configuration command. So these two are the most commonly used IPv6 assigned multicast groups. Whereas the next one, we call it as a solicited node IPv6 multicast, which is also quite similar to the all nodes multicast address, and it is actually used in the neighbor discovery protocol. This is mapped to a special Ethernet multicast address. Generally, what happens here is the Ethernet NIC filters the frame by examining the destination MAC address without even sending it to the IPv6 process. This is to check whether the device is the intended target of the IPv6 packet or not. In more terms, if we move on, now let's come to the part where we are going to try to subnet an IPv6 network. You might ask me, sir, with the vast area, with the vast expanse of an IPv6 network, what is the requirement? Why do we need to subnet this? It's not for requirement or to save the IPv6 address, and it is for the convenience of maintaining large networks into smaller groups. This is network administrators actually like to divide large networks into smaller subnets to manage them in a better manner. That is the reason subnetting is done here. So the concept, when IPv4 was first designed, there is no concept of subnet at that time. But with IPv6, it is actually designed keeping the subnetting in mind. Here, that is the reason in the very first portion, we have a separate subnet ID field in the GUA. This ID field is actually used to create subnets. The subnet ID field is the area between the global routing prefix and your interface ID. As I told you, generally we place 64. So what we have is, if you have a /48 routing prefix and a 16-bit subnet ID, you get the 64/64 prefix length. Even with 16 bits of subnet ID, we can actually create up to, if you see, we can create up to 65,536 subnets, and each subnet to support up to 18 quintillion hosts, which is quite large. So we should be least bothered about wastage of address space in IPv6. Okay. And for the easiest part here is when you try to subnet an IPv6 network, and this is a small example to give us a little bit more clarity. So if you assume that an organization has been assigned the 2001 colon DB8 colon ACAD double colon /48 routing prefix, and it is actually used to go for a 16-bit subnet ID. This is going to create these 65,536 subnets. If you see, these are all the subnets that are shown here: 001, 000, 0001, 2, 3, 4, 5, 6. In this way, all the 65,536 subnets can be created. And here only the subnet ID hextet, other ones remain the same. You see, this routing prefix remains the same. Only this hextet, which actually represents the subnet ID, is incremented. Nothing else is to be changed. So if you keep incrementing with one by one, you create all the different subnets. Okay. And this is also another example topology. But once, if you want to have a very good exposure of working with IPv6 subnetting, just check out the packet tracer activities that we have for this particular module. I will be posting the videos of those activities also, where you can have a quick look. And it's actually quite fun to work with an IPv6 subnet because it's pretty easy. You need not bother much. You simply need to increment these hextets. That's all. If you see, this is an example topology once again, which is given. And here we need 5 subnets, right? This is for 1, this is 2, and this is 3, this is 4, and this is 5. So we require 5 subnets, and you can just simply take these. You can pick any 5 subnets from the available 65,536 subnets. So let's go with 001, 002, 003, 004, and 005. So these 5 can pick them and simply give them. You see, this is what I gave them. This is the subnet ID for these 5 subnets, which I allocated to them. I can do it any manner because each of them, as I studied, it actually supports 18 quintillion hosts, which is quite huge. You need not bother about saving the address space here. Okay. And we have come to the end of this particular module. So let me just give you a quick recap of what we did here. So IPv4 has a theoretical maximum of 4.3 billion addresses only, which is which has actually exhausted a long time ago. And by usage of NAT and private public addressing schemes, we are still able to use the IPv4 address. So in order to overcome this problem, the IETF has created various, they have come up with the solution of IPv6. And to make the transition much more easier, they have created various protocols. The usual protocols of migrating from IPv4 to IPv6 fall into 3 categories. The first category is a dual stack. The second category is called as tunneling, and the third category is your translation. Okay, and IPv6 addresses are designed to overcome the problem of IPv4 lack of address space, and that is the reason there are 128 bits in length. And to make it easier, they are actually written in hexadecimal values. This is the preferred format for writing an IPv6 address, which you should get it by now. It is actually represented using columns, and this is called as a hextet. It contains 4 hexadecimal values. There are 3 types of IPv6 addresses: unicast, multicast, and anycast. Please note that there is no broadcast in IPv6, and all IPv6 unicast addresses uniquely identifies an interface on an IPv6 enabled device. And the first, in the unicast addresses, once again we have both GUA and LLA. So GUAs are globally unique and routable on the internet, whereas the LLAs enable a device to communicate with other IPv6 enabled devices on the same link and only on that link or within that particular subnet. And in order to assign an IPv6 address, you simply type it down, IPv6 address, and then write the address followed by the / prefix length. There is no writing a subnet mask or anything here. And a device actually obtains a GUA dynamically through your ICMP v6 messages. The 2 messages that are used are the router solicitation and the router advertisement messages. In the router advertisement messages, you can actually you can specify any of the 3 methods that can be used by the device to create its own GUA. If you see here, there are 3 methods. The first method being the stateless address auto configuration protocol, and the SLAAC with a stateless DHCP v6, and the third one is a stateful DHCP v6 server with no SLAAC. So the interface ID can be created either by using the EUI64 process or simply by the random generated 64-bit number. To make sure that this random 64-bit generator number that has been created by a host is unique, you also have something called as a DAD, duplicate address detection scheme. So these UIs process, these EUI scheme that we just told you how it is being done. You take the 48-bit MAC address, split into two, then insert the 16 bits FFFE in between, flip the 7th bit from the first, and then you get your 60-bit interface ID. It is the reason, or sir, which to go, either UA or randomly generated, is completely based on your operating system. From Windows Vista onwards, the current operating systems are using the randomly generated 64-bit interface IDs. All IPv6 devices must have an IPv6 LLA. Once again, an LLA can be configured manually or dynamically. To configure it manually, you simply need to write in the command IPv6, link the address which you are, whichever you have to write it down there, which starts with FF80, and then you have to mention link local there. The Cisco routers automatically create an IPv6 LLA whenever a GUI is assigned to the interface. They automatically create it. You need not specifically write it, but if you want to do it, you can do that also. There are two types of IPv6 multicast addresses. The first one is called as a well-known multicast address, and the other one is called as a solicited node multicast address. Out of these well-known addresses, once again, there are two there are two most common groups where all IPv6 devices join. The first group is called as the all nodes multicast group, whereas the other group is called as an all node all routers multicast group, which is actually joined by the IPv6 routers to exchange information. A solicited node multicast address is very much similar to the all nodes multicast address. This is that because we can, the main advantage is that we can actually map it to a special Ethernet multicast address. Because IPv6 was designed keeping subnetting in mind, a separate subnet ID field in the IPv6 GUI is used to create the subnets. Usually we have the 16-bit subnets, or one particular one hextet is reserved for the subnetting part. So with this, we come to the end of this particular module. So please have a quick look through. This is quite good information on an IPv6 address, how to work with them, what are the different types of IPv6 addresses, and also how to subnet them. Please do follow or do watch the activity videos that I'm going to post for this particular module, where you can work with an IPv6 address and also do the subnetting on IPv6 address, just like how we did with the IPv4 addressing in our earlier module. So with that, thank you very much.